Perfect. Hello. Good afternoon, all. Thanks for coming. My name is Kash Saba. I'm a senior consultant with Microsoft. I've been supporting the Department of Veterans Affairs over the past couple of years on this specific project that we're going to share with you.
Great. Spencer Schaefer. I'm the Chief AI Officer for Region 15, basically in the Veteran Affairs Administration on the health side. I'm also a clinical kind of solution architect for the National Artificial Intelligence Institute. The way I got involved in this particular project was we've been trying to scale up and have opportunities not only to improve kind of operationally how we stream data, but also to help support like real-time machine learning AI models. So should we go the right way? Why are we talking about this? Veteran Affairs is a very large organization. We have an opportunity to have one of the largest databases of healthcare for sure in the world. We have 9.1 million patients, 2 million claims per year. We have 1,200 active medical facilities. Of that's 152 actual hospitals. Over 120,000 clinicians. We train over 75% of all the MDs and DOs in the country. At one point in time, as they do the residency, they come through the VA. We have over 1 million now full genomic donations between DOD and VA patients. And we have over 450,000 employees. So when you think about that, you know, and you maybe earlier come and see like a Joe D'Oria talk or others in OINT, like we're talking a scale of 450,000, you know, and so it's a very heavy lift that we get to. So what is the project? The project is, you know, we've kind of been stuck in the in-between of having the ability to use and have access to real-time clinical dynamic data and the kind of traditional data warehousing technology for quite a while. You know, 10, 15 years ago, as we stood up the corporate data warehouse using SQL servers and so forth, it was very, very ahead of its time, right? Like huge, I think we have like 8,000 servers or something. I don't even know, it's a ton. And it's like 40 petabytes of data. We have 75 petabytes of actual images on data. And so very robust, very good, but the issue is like kind of over time, the ETL process was never able to speed up more than every 24 hours, right? And so, and the other time is we on the health side use HL7 messages. Well, that's just a very small subset of the data. And so we've been trying to work through how we can overcome this. Here's a little timeline on some recent stuff. In May 2018, Cerner was awarded a contract for the Department of Veteran Affairs. I'm sure nobody here has heard of that contract or anything. We continued to work through getting those sites up. With that became the understanding that we're going to have even more syndication than before because we're going to have many new sites on Cerner. How do we pull them together? And that's whenever our kind of core foundational data extraction methodology from Vista rolled into the HRM program. So in 2022, data migration syndication team launched. In October, there started to be some discussion of strategies for Azure Databricks to be involved to help stream the information. November, professional services onboarded through Microsoft Customer Experience Services team. And then 2023, we had like the streaming became online. And then today, we'll talk about kind of where we're at and what kind of opportunities we've had to use the data.
Awesome. Thank you, Spencer. So the life cycle of an electronic health record, or EHR, starts at one of the 130 Vista EHR systems, right? At a regional data center. And from here, the data gets synced to the Austin data center into a VX130 master, which is a InterSystems Iris database. And a copy of the database is also made in the Azure environment. As the records make their way into the Azure environment, they interact with several Azure resources, right? And all of these Azure resources and the subscription are hosted within Azure Government Cloud. At the very center, you will see an Azure Data Lake storage account, which serves as the primary storage facility for the electronic health records. And we have an Azure Databricks, which serves as the compute layer. In addition to these, we also have several supporting technologies or resources that are used. For example, Entra ID, which stores all the developer information and securely creates AAD groups. We have Azure Data Factory, which stores all the link services, data sets, and pipelines that are used for orchestration for all the ETL jobs. We have a GitHub repository, which serves as the code base. All of our code is written in Python notebooks, right? With the exception of a couple notebooks that use Scala. We have Key Vault, which stores all the secrets to the keys. For example, service principal secret values are stored in the Key Vault. Some of the service principal credentials are stored in the Key Vault. The login information or the login credentials for the Azure SQL database are stored in the Key Vault, right? Similarly, we have Azure Monitor, which monitors the logs, the triggers, and the runs for the Azure Data Factory, right? And finally, we have the Azure SQL DB, which serves as the config DB for the entire model runs. All the parameters are stored in the Azure SQL DB and are retrieved during runtime. The Azure Data Lake storage itself is modeled after medallion architecture. For example, we have a landing zone container similar to the bronze layer, right? We have a raw zone container, very similar to silver layer, and then we have the consumable refined zone container, similar to a gold layer. As the electronic health records make their way into the Azure environment, they are dropped into the landing zone container in JSON format by an API engine, and the API engine sits on an inner systems ensemble VM. From here, we primarily run two transformations that move the data from landing JSON to ready to be consumed Delta format in the refined zone container. The first transformation is called autoloader process, and this is the streaming processor that we built, which takes in all the JSON messages that come in and moves it into the raw zone container in Delta format. The second transformation is called merge process, which takes all the records in the raw zone and does a merge operation into the refined zone and keeps the data in the refined zone current so users can consume it. The data or the electronic health records that sit within the raw zone have duplicates in it, right? And that's by design. We have a customer right now who wants to consume data in its raw format, meaning with duplicates in Delta format, and that's why we've enabled that. But as the data moves from raw zone into the refined zone, the data gets deduplicated and it's ready for consumption. We have enabled sharing across two teams right now, and both the teams have their own Databricks instances, right, and service principals. So we've enabled ACL and RBAC role-based sharing, basically provided their service principal a specific ACL role on some of the folders within the refined zone container, if you will, so that they can read the data and have access to all the data that's current in the refined zone container. We're working on a scalable sharing mechanism right now, and hopefully we'll have that ready in the next few weeks. The electronic health records primarily are consolidated into about 1,400 tables. So we had to do a historical ingest across these 1,400 tables to start with. To move that data from JSON format in landing zone to Delta format in refined zone. That was about 200 billion records, right? Just the historical ingestion up to a specific timestamp. And on top of that, we built the autoloader processor and the merge process. The autoloader process itself streams about 40 to 60 million records on average right now, and that number could go up in the next few months. And it's heavily parameter driven. What do I mean by that? Parameters such as the table name, right? The column name, the column data type, all of that information is stored in the config DBs, the Azure SQL database, and are retrieved during runtime. And we use Databricks Workflow API, right? We use the Workflows API to create these jobs, deploy the jobs, and also monitor the jobs so that we know if something errored out, we would know about that specific job, right? The merge process is slightly different. It basically takes all the records in the raw zone and deduplicates them based on key columns on a table basis, right? And merges, basically updates or inserts that data into the refined zone. We use Azure Data Factory orchestration to run the merge process. For example, we have a couple pipelines that are triggered daily. And these pipelines in Azure Data Factory basically invoke Azure Databricks notebook jobs so that the notebooks itself will run the merge operation, right? And all these jobs are run on cluster pools. So we've set up several cluster pools across the board that can be shared across both the autoloader and the merge process. And both autoloader and merge process are parameterized by tables and also by clusters, right? So depending on how large a table is, a specific cluster gets spooled, the job gets run, and then the cluster shuts down. And I'll talk briefly about this in the next few slides. So some of the best practices we have implemented are, we use Azure Databricks Workflows API, as I was talking about, and we use Python SDK to create these jobs, monitor them, and deploy them across the board. Since we were working with many tables, we realized it'll be easier to consolidate the tables into groups, and all of this could be done within the Azure SQL DB as param, so that during runtime, we retrieve a set of tables as part of groups and do the processing, right? And I'll touch on this in the next slide. We've used shared cluster pools in conjunction with the groups of tables, right? Again, I'll talk about this in the next slide. But most importantly, we have enabled change data feed in the autoloader process. So as the records get streamed from the landing zone JSON format to the raw zone Delta format, a change data feed version and timestamp gets added to every record. This helped us immensely in running the merge process downstream, right? So instead of looking at every record in a specific table in the merge process, now we only look at the most recent records. For example, if I'm running the merge process today, I don't have to look at all the records, but I only look at the records that have arrived after my last CDF version timestamp, or a version number and timestamp. So we take the CDF version as a watermark so that it gets updated every time a merge process is run. So we're running these jobs more efficiently, cost effectively, and they run much faster, right? So we realized as we were working through this process that there is no one cluster size that can rule over all the data, right? Hence, we had to get creative with assigning different tables with varying volumes, number of columns, and the column widths to different cluster types, right? For instance, we had several large tables. So large tables that are in tens of billions of records are distributed across large cluster pools, right? Tables that are medium fact tables and medium dimension tables that are of hundreds of millions of records are distributed on a medium cluster pool. And small dimension tables that are in tens of millions of records or smaller are distributed across small cluster pools. So this is where the table, the binning of tables into groups concept was very helpful, right? I was talking about in the previous slide. So if we were to, we could bin about, let's say, 100 large fact tables into group one, right? So that we could deploy for the autoloader process, we could deploy all of those 100 large tables on one single cluster pool. Similarly, if we created a second group with medium fact tables, right, with 100 medium fact tables, that all those 100 medium fact tables could be deployed on one medium cluster pool. Same thing for small cluster pool, right? So now all of a sudden, instead of us spooling up about 1,000+ clusters to run these 1,000+ table jobs for the autoloader, we're only efficiently using about 10 clusters or so, right? This helped us in two fronts. The first being, obviously, the cost, right? Instead of spooling up 1,000 clusters, we were, like I said, spooling 10 or 12, so the costs were significantly lower for the customer. On the second front, we share this subscription with several other peers, right? Several other teams that are working on this with their own database cluster pools and all-purpose clusters, and they're doing their own work. We didn't want to impede in the work they're doing, right? So every subscription gets their own virtual CPU limit, right? If we would have used 1,000+ clusters, we would have exceeded that limit. And sometimes our peers who are working on like mission critical projects, you don't want them to see like a quota exceeded error on their cluster when they try to spool it up, right? So doing something like this really helped us stay within, I guess, our limits, right, of virtual CPU, the number of virtual CPUs that are assigned to our specific subscription. So in summary, shared cluster pools really helped us keep the cost down for the customer and stay within the limit for the virtual CPU counts. So if you saw the fireside chat this morning with Ali and Jensen, they were talking a little bit about accelerating Photon to speed things up. This slide basically proves some of that, right? This slide basically, the table and the column plots show the impact of Predictive IO paired with Photon 14.1 engine on two large tables. And this is for the merge process, right? The second transformation process. So on the left, you see a table called order action. On the right, it's a table called lab chem. These two are two of the largest tables that we were working with. There are several others, but order action has about 10 billion records in the refined zone, right? Lab chem has about 14 billion records. So if you look at the very first record for order action on 131, to merge about 3.4 million records into a 10 billion record set, the merge process took about 72 minutes to run, right? And this is with change data feed enabled, right? And if you look at the middle record on 2.6, to merge about 4.6 million records, it took about 14 minutes. That's a huge improvement in runtime, right? The difference between 131 and 2.6 is for 2.6, we've enabled Photon 14.1, which was the most recent Photon version available in government cloud at the time, like this February, I believe. But if you look at the last record on 2.13 for order action, to merge about 3.8 million records, it took just under 7 minutes. I mean, that's a huge improvement. The difference between 2.6 and 2.13 is on 2.13, we've enabled Photon 14.1 in conjunction with Predictive IO. So Predictive IO paired up with Photon 14.1 provided huge improvement in runtime, right? The story is exactly the same for the second table, lab chem. If you look at 131, 2.7 million records merging into a 14 billion transactional record set took about 80 minutes. And at the very end on 213, to merge about 2.6 million records took 8 minutes. So this definitely helped us cut costs down, especially when we were doing the merge process, right? So this next slide builds on the previous slide. I won't go into both tables. I'll just talk about table one. If I take the first record, right, the CDF only, that's the base version. To merge about 3.4 million records, the merge runtime was 72 minutes. But then when we ran CDF enabled with Photon 14.1, the number of records that were used to merge increased by 28%. So, and then the merge runtime decreased from 72 minutes to about 15 minutes. Well, if you just look at the merge runtime, that doesn't give you a clear picture. So if you just look at the efficiency, the last column from the second last column, I guess, you could look at the weighted efficiency, right? The model improved about 6.5 times when we use CDF plus Photon 14.1, when the records went up by 28%. Similarly, when we use Photon 14.1 paired with Predictive IO, the records went up by 30%, but the merge runtime was only 7.5 minutes. That's about 13 times improvement, right? If you look at the number of records paired with the efficiency in the runtime. So we were seeing huge improvements with Photon engine, the latest Photon engine, when paired with Predictive IO across the board, right? This is just one table, but we had like about 150 to 200 large fact tables and billions of records. We were seeing this consistently, the improvement consistently across the board. So this was a huge win for the customer, right, in terms of cost savings and being efficient and have those clusters pools be used by other teams, right? Again, this slide talks about it's a key takeaway, really. Like, we had a legacy method, to give you guys some background. We had a legacy method before we implemented CDF that was using file listing to do the merge process. So we were looking at the number of files that came into the raw zone, right? And then taking the timestamp from ADLS and using that timestamp as the watermark. And as the file sizes increased because of small files problem, that process was just taking forever to run. So implementing change data feed and incrementally including Predictive IO with Photon 14.1 on average reduced our runtime by a factor of 8, right? So definitely a huge improvement for the merge process and for the autoloader process as well. And this was a big win for the customer. I'll pass it to Spencer at this time.
All right, thank you. Appreciate it. So as you can tell, it's been a great journey for Azure and for Databricks to kind of come through this. I think it's been exciting on my end as someone who has been kind of waiting for this for a long time to see how they've been able to scale and make those iterative changes. I can tell you from a data science and kind of analytics standpoint, even before having this done, using the SDP platform, Summit Data Platform, we can share some like use of Photon too, where we've seen decreases from 7 hours for a query on our previous SQL data warehouse servers to the infamous Ching up front, getting that same query down to 32 seconds. And so like we're really enjoying kind of that experience. I think the other thing we wanted to kind of talk to is I wanted to give a credit not only to SDP, but also out to Dr. Toronto and his team over on EHRM. All of their historical development and work with the VX130 process. 130, as you might kind of think, is representative. There's 130 different individual medical record systems in the VA, right? So we have 130 instances of what we call Vista. So that gives you an idea of not only how much it ties together, but as I lead into the next slide, it'll kind of give you an idea of like why it's so important for us on the clinical operations side to not have to deal with 132 separate HL7 interfaces that represent 18,000 logical links. So as we were going to EHRM, unfortunately, that was one of my first jobs, and that was to evaluate all 18,000 logical links and say, do we need them or not? Will Cerner support this or not? And in doing so, what's ironic is from an outside the medical record and medical device systems, this does away with that, right? I mean, like it helps us come all those, 18,000 links, which cover maybe 20% of the data, if that, down to 1. And so real short here, just kind of give you an idea. Summit Data Platform and some other partners have really helped the National Artificial Intelligence Institute, and then our local group, which is just medical informatics, data science, and emerging technologies out of Kansas City in Vision 15, have really helped us kind of put together a much more consolidated architecture of data and gets away from many different systems to us being able to kind of just honed down into not only a traditional HL7 pathway, which we can use event hubs, but eventually transition into using this new stream. And the other thing we want to talk about is like, what are some of the actual use cases? This here is what we call the Digital Command Center. It was one of the first priority projects from the National Artificial Intelligence Institute. And the reason that we put together the concept of Digital Command Center was not only because we know in healthcare operations, clinical operations, that we need to be able to direct traffic, to have an idea of how systems are going in the hospital operationally, but we also needed a way to start delivering machine learning to the end user, right? And so we kind of went across this approach of like, let's build out a methodology of not only creating multiple different end user tools, but with the underlying architecture so that we can also deliver the outputs of our machine learning models with it. This one here is just simple. For a long time, we were held back on being able to do a literal like inpatient medication bed flow control system because we didn't have near real-time data flowing through. We could leverage some HL7 interfaces, but it was limited to just admission data transfer, admission discharge transfers, some labs, and a few things like that. Now, since we've been able to connect, and this is the first use case that I'm aware of the actual streaming coming through, is now we're able to, within a few seconds, usually, be able to have all those different activities that are recorded in the Vista journal logs that are being streamed over to go into the system, and so that we can actually begin to help push patients through the system, help our clinicians make decisions on what is our access going to be tonight. Do we need to go on discharge, our diversion, et cetera. Next one is the one that we've been working on for a couple of years to get in. This is a really exciting project. We've gotten a lot of support from the White House and through the Undersecretary's office. This is a project where we partnered with a third-party vendor called Agile MD. Agile MD had gone through and kind of had several different iterations of creating a clinical deterioration risk score for inpatients. In healthcare, we have a couple of these that have been shown to be, pretty useful, but they still had a lot of opportunity for improvement. If you're looking at like an AUC standpoint, the ones that are currently utilized that are non-machine learning are like a 0.72 AUC, et cetera. We're seeing this up at over 0.9, maybe 0.96, depending on where we get to. And so where we're excited about this is it not only uses these general features, 5 or 6 features that you would see in these other models, we're using 70, 80, 90 features in this machine learning model. The gap was, how the hell are we gonna where are we gonna find the 70, 80, 90 features that are needed to make it work well? And where we've been able to resolve that is a couple of different. One is just the basic streaming that they've been able to provide now with more data. The second is the progress notes, right? Like progress notes, PDF files. These have been the holy grail of like where the real semantic understanding of the patient exists. While they've been working on this project, we've in parallel been working through some large language model extractions and et cetera. And we now have a multi-agent model that not only will pull the medical entities out in real time as it's streaming, but also utilizing expert agents and et cetera, is able to do these very complex calculations of other scores that a patient needs, like a skin integrity score. All these very difficult kind of like mathematical equations that have relied upon very semantical understanding of kind of complex thought, chain of thought, we're able to now do. And so we're actually able to like truly begin to build these incredibly precise, accurate machine learning models because we were able to provide it with the actual data that we've never been able to before. And so very excited about that. And just a quick thing, like the reason this is so important is in a 4-hospital community setting, the model that we have retrained in for VA, it performed that 1 in every 3 patients with sepsis, it reduced the mortality in 1 in every 3. So think about that. Like, we have thousands of people, every couple of years die of sepsis in the VA. So 1 in every 3 of those potentially, according to their community data, could have been prevented. Finally, just for the last minute or so, what are the key takeaways? I think we know that Delta Lake makes a format makes for a much better and easier consumption downstream for analytics. I would also venture to say that something that gets overlooked is, like, honestly anymore, I don't care about the analytics too much. Like, we want to deliver real actions to people, and I think this is what we're able to see is we can now support like real actionable events downstream, and that may come across as like a dashboard or et cetera, but within that dashboard you're able to take actions and so forth. It increases the ease of use of libraries. What's exciting about this for us is that your libraries in a notebook can be multi-different language, right? Like many different languages can be used in one notebook. It allows us to collaborate on a level we haven't ever been able to before. Use data scientists with different different models, et cetera. And then we have a seamless sharing of the data, obviously. Why is it important for care delivery? We talked a lot about it. Instead of having 18,000 streams coming through and getting part of your data, right, we can now connect into a single stream that comes through. It eliminates expensive and complex HL7 integrations, as well as facilitates novel new methods of medical entity extraction. And this is where I think we got some super exciting things on the horizon of how we can really begin to take the next step here.
Yeah, and yeah, thank you, Spencer. And in terms of cost savings and efficiency, right, it's something I was talking about, like as we used config DB-based params, right, to group tables, for example, and deploy several tables for the autoloader process onto a single cluster, that's huge, right, in terms of cost savings for the customer, and also being efficient and being able to reuse those clusters for other use cases, and other peers can use them for other projects and such, right? And merge process as well, right? Like using Predictive IO, for example, and the Photon, most recent at the time, 14.1 engine, significantly reduced our costs in terms of runtime, right, on a daily basis, and that on average saved about $12,000 a month for the customer. So on average, in terms of being efficient and cost effective, we think that Photon 14.1 paired with Predictive IO and shared cluster usage was very helpful for the customer. So I guess that's our presentation. We'll be happy to take any questions you may have.